Remember that this week we're going over the mathematical background for this course and how we connect it back to the underlying representation on a computer. Today we're talking about matrices and vectors.
Why are we talking about vectors and matrices?
Vectors and matrices provide us with convenient ways of representing the mathematical concepts fundamental to this course, and we'll need to be able to interpret the basic language of linear algebra to read the material in this course.
Let's start with vectors. What's a vector?
The simplest definition is that a vector is a list of numbers. Like in Python, you can access elements with an index, although it's written a bit differently. They're usually written as subscripts, the indexes, and annoyingly sometimes they're indexed with 1 rather than starting at a 0, as we do in Python and other programming languages.
That's it?
We can write the numbers horizontally, in which case we call it a row vector, or we can write them vertically, in which case we call it a column vector.
What's the difference?
The difference is one is written horizontally and the other is written vertically.
Okay, but they represent the same thing?
In linear algebra, we would say that row vectors form the row space and column vectors form the column space. But we only care in this context about whether the vector is a row vector or a column vector when we want to do some kind of operation on the vectors, like multiplication or addition. We call lists of numbers vectors and single numbers, not part of a list, scalars.
Okay, we all know how to add and subtract numbers. How does this work for vectors?
It's simpler than you might think. First, the vectors have to be the same size, and they have to be both row vectors or both column vectors. To add them, we just add the individual components in the vectors.
That seems easy.
We haven't talked about matrices yet, but the same thing holds for them.
What about multiplication?
Well, it depends.
I was afraid you were going to say that.
It's not so bad. If you want to multiply a scalar times a vector, it's even simpler than addition. You just multiply the scalar times each element in the vector, and then you're done.
Okay, that was actually simple.
Yeah, but when we talk about multiplication, we really need to be more specific. What people usually mean is the dot product. The dot product is only slightly more complicated, and we can take the dot product of a row vector and a column vector of the same size. The result is a scalar. Suppose we have two vectors, a and b, and both have two numbers. To take the dot product, a dot b, we just take the sum of the products of each element in each vector. So we take element 1 in A and multiply it by element 1 in B, element 2 in A times element 2 in B, and then we sum these products, and then we have the dot product.
All right, that's simple enough, but why?
Well, as in many things in mathematics, there are also geometric interpretations of vectors that we should discuss. If you think about it, there's something else in mathematics that looks suspiciously like a list of numbers.
Like coordinates.
Right. So one way we can think of a vector is a set of coordinates in a space. We say that the number of elements in the vector is the vector's dimension.
Because a vector with n-dimensions must be in at least an n-dimensional space.
Right. If we have a two-dimensional vector, this is equivalent to a point in a 2D Cartesian plane, which we can call R2.
Is there some difference between vectors and coordinates?
There is, if you want there to be.
What does that mean?
Well, we usually think of vectors as having a direction. A coordinate is a point. A directional vector is pointing in the direction of that point from the origin in the space. You can think of it in whichever way is convenient at the time, because these representations are equivalent. The math works out either way, but often when people talk about vectors, they're assuming some kind of directional interpretation. Even so, a vector is just a list of numbers, and you can interpret them either way.
So how does this relate to the dot product?
Well, there are nice geometric interpretations of vectors, whether you imagine them as having directionality or not. Let's just assume that they do. Then geometrically, a dot product is a measure of how much two vectors overlap. If they overlap a lot, the dot product is big. If they're orthogonal, the overlap is 0.
What's orthogonal?
It's when two vectors are at a right angle to each other. In 2 dimensions, they are perpendicular. In more dimensions, it becomes a little more complicated. Orthogonal vectors are those that you can put into some plane such that they're perpendicular. It might be easier to see this by writing a dot product in terms of the angle of two vectors. The dot product is the length of the vectors times the cosine of the angle between them.
But as you say, you can look at two vectors in 2D and tell how much they overlap. But how do you do it in 3 dimensions?
Remember, you can only take the dot product of vectors that are the same dimension. For each coordinate, you multiply the coordinates together and then add it all together.
So that's what it means geometrically and mathematically. But what does it mean intuitively?
One way of looking at dot products is as a similarity measure. Let's say that you have a big vector where each coordinate is how much of the document is made up by a word.
So there's a coordinate for dog, one for cat, one for rutabaga, and so on.
Right, thousands of dimensions. If the documents don't share any words, then the dot product will be 0. If the documents are the same, then the dot product will be 1.
That's only if the document vector's length is 1, right?
Right, and we'll often do that to make a dot product a similarity metric between -1 and 1. But this is just a kind of multiplication. It gives a single number. But we can do multiplication that creates a new vector or matrix as well.
If you want to see more videos like this, check the video description for the course that comes from the link down below. You can then see the context and the correct order for watching these videos. YouTube will gleefully show you stuff in the wrong order. If you want other people to see this video, provide a big gradient to the recommendation algorithm by clicking the like and subscribe button down below.